this class. All right, okay, so let's first finish the last two questions. Okay, last two questions. Okay, so in the worksheet. Okay, the first one is kind of the yin and those yang. Okay, so and so you need so you need the first find which function group has highest parity. Okay, so for this one, definitely alcohol. Okay, so in this case, we'll name this compound based alcohol, give the alcohol lower number. Okay, so that's here 1, 2, 3, 4, 5, 6. All right, six carbons. Okay, that's here the hex. All right, and then there's the double bond and the triple bond. We need to give their location number and those their name. 3 in five I, okay. All right, and then in the end, okay, alcohol, okay. So alcohol, just keep in mind, okay, so that's the location number. You also need to give alcohol number, location number, okay, that's 3 okay. And then 14 just take off this chloro substance group, okay, so that's 4 chloro, okay, so that's the full name, okay. Right, and then from now on, you also need to label the stereochemistry. And so this double bond case, so that's the two higher party group case, so it's here and then here. On the same side of the bond case, so that's here we need to label at kind of Z, okay. Yeah. Z. All right, so for next one case, it's a diene case, so but here the ketone has a higher party. Ketone has higher party, okay. So in this case, we give the ketone, the lower number, okay. So that's from left of the carbon chain, okay. So all right, 7 carbons, okay. And then that should code kind of hapt. All right, so that's because this is the diene, we need keep here the A, okay. Hapta. And then give a location number for the diene K 3, 5 diene K. All right, so ketone, okay, so please keep in mind, okay, CC double bond, CC triple bond, ketone, alcohol, and also here the amine, okay, these 5 functional group, okay, so no matter where are their positions, okay, you need to give location numbers, okay, so so that here should be 2 on, okay. And then no done yet. Okay, so there are kind of theta bond. Both have kind of cis trans isomers. You need to give their kind of the assignment. Okay, so first one that's definitely kind of the Z. Okay, so that's 3Z. And then next one that's kind of trans. Okay, so that's 5E. Right, leave some kind of in the parentheses before the whole name. All right. And then next one is kind of the ring structure. Okay, so both chlorine and also ether kind of the low part. Okay, compare with kind of the ring structure. Okay, so that means this one we based on kind of the cyclohexene to name it. Okay, right. And then alphabetic order put the chloro and also this methoxy. Okay, so that's alphabetic order. This is 1 and this 3. Okay, so that's 1 chloro 3 methoxy. Okay, so a little bit, small space. Okay, 1 chloro, 3 methoxy, cyclohexene. Okay, right. So there are kind of two steric centers in this molecule. We need to give their assignment for individual one. Okay, so chloro has highest one, highest party, and then followed by this branch. Okay, so this branch. Okay, so although the first layer CH2, CH2 same. Okay. But your next level, okay, so this is H2, this one has kind of oxygen, okay, so that's a higher one, 2, and then 3, okay. So 1, 2, 2, 2, 2, 3, that here looks like here the counterclockwise, so that means for this, CR center should be kind of the S, okay, 1 S. All right, use another color, okay. So for another one, okay, so highest one should be kind of this oxygen, 1, and followed by this branch, okay, that's 2, and then followed by this branch, okay, 3, okay. All right, so if you draw the arc, looks like here the clockwise, okay, so 1, 2, 2, 2, 2, 3, okay. But here the this hydrogen can actually kind of point towards you. You need to give opposite assignment, okay, opposite assignment, okay. So that here means here for this molecule, okay, so that here 1s 3s. Yeah, all right. So that's here naming, okay. And so next one is kind of most difficult one, most difficult one. So this one is kind of has aldehyde, amide, okay, cis bond, and also ketone, and also a methyl group, okay. So amide has highest parity, so that means we'll name this compound based on amide. So that's here you can circle this part. So we gave the amide name first. All right, so amide is a terminal functional group, okay? So that means we can start with this carbon, okay? So that's here the carbonyl carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons, okay? So that's here should call noning, okay? So there's CC bond, okay? So then you need to change AN to EN, give their location number 3 in amide. Amide terminal functional group don't need give their location number, okay? And then we need to take off the starting group, okay? So there's the ketone, there's kind of methyl, okay? So ketone, prefix name is called oxo, okay? So and then there's one methyl on the nitrogen, one methyl group on the carbon chain, okay? So these two we combine them together, okay? So that's N7 dimethyl, okay? So our particle there, okay? And then 6 oxo, okay? Right, so that's still not done yet, okay? So in this molecule, there's CC bond showed kind of E configuration. There's also kind of CR centers, okay? So we do one by one, okay? So that's here should be 3E, okay? And then for this CR center, okay? So high C is this branch, okay? So that's 1, followed by here, 2, and then followed by here, 3, okay? So the 1, 2, 2, 2, 2, 3, okay, looks like the counterclockwise, okay, so that means kind of should be S, okay, so hydrogen point away from you, okay, yeah. Right. If you have any questions, just please type in the chat window, okay, so right, so that's here the 7S, that's the full name. All right, okay. So next one is kind of maybe you guys tell me the answer, okay? So ask whether these two molecule are enantiomer or kind of these two are enantiomer not, okay? So let's do this, okay? So just here for the first pair, okay? So type your answer in the chat window. Are they enantiomer or not? Anyone want to take a try? Oh. All right. So both yes and no. Okay. All right. So just keep in mind. Okay. So for enantiomer, okay, for this pair, okay, there are kind of three stair centers. Okay, three stair centers. Okay, and so enantiomers, all three stair center should show opposite kind of configuration. Opposite. Okay, one is kind of dash, another has to be wedge. Okay. So for those two molecule, okay, actually you don't need design RS, okay. So you just kind of rotate one molecule, okay, to see whether they can match to each other or not, okay. Right. For example, I just rotate this right molecule like 180 degrees, okay. Yeah, like 180 degrees, okay. Right. So once I rotate it, okay, so then this dot bond will go to the left, okay, and then this bond will go up, this bond will go down, okay. And then this bond we could still dash go to just the 180 degrees, okay. Right. So if I show this way, you can clearly see, okay, so for all three stair centers, okay. Here dash become wedge, wedge become dash, and then dash become wedge, okay. So all are opposite, okay. So all opposite, okay. So that means they are enantiomers, okay. Yeah, so that's yeah, the something please keep in mind. Okay. And the similar thing for these two, okay? So these two cases, yeah, if you take first look, you find, okay, one's the dash, one's the wedge, okay? So yeah, they are kind of enantiomer, okay? Okay, so yeah. So yeah, you need kind of yeah, rotate or flip, okay? So yeah, for these two actually kind of yeah, you can flip one molecule, okay? So for example, yeah, I flip, okay, just like this way, okay? Yeah, flip the whole molecule, okay? So if I flip it, okay, and then yeah, so yeah, if yeah, you flip the one molecule and then this yeah, the yeah, dash bond, wedge bond will become dash, okay, because kind of yeah, the original like this way, and then not kind of yeah, going inside, okay, and it's two, okay. So finally, yeah, these two, yeah, actually same molecule, okay, so that's identical, okay, so yeah, not enantiomer, okay, these two, yeah. So that's yeah. Please keep in mind, okay, so yeah, for the molecule, you should able to kind of yeah, rotate, flip it, whatever you want, okay, just yeah, make sure get kind of yeah, right answer, okay. So if you still have difficulty kind of yeah, yeah, visualize the molecule, no problem, okay. So you can write RS, okay, write RS, okay, so yeah. For example, yeah, these two molecule, okay, so if you write RS, okay, so that one should be S, okay, this steric center S, okay. This steric center also be S, okay. So you find kind of, oh, actually kind of, yeah, these two have yeah, same configuration, okay. So that should be identical, okay. Yeah. All right, okay. So here comes kind of your first important conclusion, okay, for the yeah, identified kind of your stereoisomer, identical, and actually also yeah, the yeah, diastereomers, okay. So yeah. So yeah, if yeah, there's only one yeah, chiral center, right? Write down, okay, write down, okay. If there's one chiral centers, okay, and then yeah, yeah, only two possibility, okay. So yeah, yeah, I mean the relationship between the two molecule, okay. So yeah, it's kind of yeah, you compare the relationship between two molecule, okay. So yeah, if yeah, these two chiral center, yeah, opposite, okay, one's R, one's S, okay. Then this yeah, the two molecule will enantiomer, okay. So yeah, if yeah, these two kind of yeah, these yeah, two chiral centers, okay. So yeah, the two same chiral centers, okay. So same configuration, then they we called kind of identical, okay. So last year, just I showed yeah in the last example, okay. Right. So more difficult is kind of a multiple, okay, chiral center. So multiple chiral centers, okay, so yeah, if all are kind of yeah, opposite, okay. Yeah, so like I showed it in the first example, okay. Then yeah, these two will be the yeah enantiomer, okay. Right. And if we are all kind of yeah, same, okay, so that yeah, either also yeah, the yeah, identical. Right, identical, okay. Right, and the last one kind of yeah, some are same, some kind of opposite, okay. Then we come to kind of yeah, the diastereomer, okay. So that's yeah, the yeah, pretty important conclusion, okay. Right, right down, okay. So that's yeah, the yeah, fundamental yeah for this yeah, the yeah class, okay. So yeah, we will later have a lot of questions, okay. So yeah, ask you compare the relationship between the two molecule, okay, and then you should able to yeah, the figure out yeah, the yeah, which is kind of yeah, the enantiomer, which are kind of yeah, the yeah, diastereomer, okay. All right, so let's continue our kind of yeah, the yeah, lecture, okay. So how do I do this? Hmm. Okay, and so yeah, last time I just mentioned, okay, so yeah, the yeah, Two possibilities, okay, so we actually kind of for the diastemaers, okay, so could be cis trans, okay, or could be kind of yeah, multiple stair centers, okay. And then previous example, okay, I showed you guys yeah, those yeah stair centers, okay, so have a different attachment, okay, so like this one, OH group, okay, and then CR, OH and CR, okay. So that yeah, you should generally kind of the 2 to N kind of yeah, 2 to N kind of the stereoisomers, okay, so yeah. But one tricky thing, okay, one tricky thing kind of yeah, you have identical kind of yeah, stereocenters, okay. So what's mean identical, okay? So yeah, a substitute group are same, okay. So for example here, okay, so yeah, the top here stereocenter has yeah methyl, hydrogen, chlorine. Bottom stereocenter also has yeah the methyl, chlorine, hydrogen, okay. And then yeah, you need to be careful about yeah, these kind of situations. Okay, all right. So yeah, looks like yeah we still can generate kind of yeah yeah two pairs of enantiomer. Okay, so yeah four isomers, totally four isomers. Okay, so S S R R. Okay, and then R S and those S R. Okay, so yeah yeah wait then R S. Okay. And then the SSRR definitely kind of yeah, the enantiomer to each others, okay? But bottoms one actually kind of yeah, not enantiomers, okay? So reality they are same compound, they're same compound, okay? So yeah, just you rotate one molecule like 180 degrees, okay? For example, yeah, you rotate the right molecule like 180 degrees, okay? And then yeah, the chlorine will go to yeah, the right, and then you find yeah, these two molecules actually superposable, okay? Superposable, actually, they are kind of yeah, same compound. Okay, and if you take a second look, yeah, you find kind of yeah, yeah, for this yeah, the bottom kind of a molecule, okay, there are yeah, the symmetry plane, okay, symmetry plane. So yeah, if one molecule have one symmetry plane, okay, pass through kind of yeah, middle of yeah, the carbon bond, okay, the carbon two, carbon three, okay, and then half is mirror image to another half. Actually, this molecule is achiral, okay. So now we come kind of yeah, yeah, very important kind of yeah, compound called the meso compound. Okay, so yeah, so for meso compound, okay, so yeah, there are kind of yeah, two or more chiral centers, okay, and then yeah, yeah, but the overall the whole molecule is kind of achiral, okay, there are two or more, and uh, one thing could be sure, okay, so yeah, if one molecule is yeah, yeah has only one chiral center, this molecule has to be chiral, okay, but yeah, if two or more chiral centers, okay, then no necessary, okay, so yeah, because of meso compound, okay. And so yeah, if we are molecule with yeah, the n steric centers, okay, so that yeah, maximum kind of yeah could be yeah, 2 to n kind of yeah, yeah, stereoisomers, okay, but yeah, because of meso compound, yeah, reality could be less than kind of yeah, the 2 to n, okay, so yeah. Right, and then we work on maybe two practice case yeah, here. Hmm. Oh, here, okay. All right. Okay, so yeah, you guys take a try, okay, work on the question two and the question three in the yeah worksheet. Okay, so I gave out in the last lecture. Yeah, question two and question three. Okay. So question two had yeah four compounds. Okay, so you need to determine relationship between one and two, and also yeah three and four. So are they enantiomer or kind of yeah diastereomer or yeah yeah identical? Okay. Yeah, we can do it one by one. Okay. So type your answer in the yeah chat window. Okay. What's the relationship between one and two? One and two. Are they enantiomer or kind of yeah the diastereomer or yeah just identical? Right. Type your answer in the yeah chat window. Yeah, that's right. Okay. So all right answer. Okay. These two are enantiomer. Okay. All right, so yeah, the star center or opposite, okay, and then actually kind of mirror imaging, okay, so yeah, and then non-super impossible, non-super possible, non-super possible, okay. All right, so now it comes kind of tricky one, okay. So what relationship between kind of yeah 2 and 4? Sorry, okay, 3 and 4, 3 and 4. Type also your answer in the chart window, okay. What's the relationship between yeah 3 and 4? Are they identical, enantiomer, or kind of yeah the yeah diastereomer, okay. All right, pretty good. Okay, so all you guys can know the trick. Okay, so these two actually identical. Okay, right, identical. Okay, and the reason for that kind of yeah, the actually yeah, looks like yeah all opposite two cell centers. Okay, but yeah, if you flip one molecule like 180 degrees, okay, so exactly match the original one. Okay, so that's actually kind of yeah, identical. Okay. And if you kind of yeah, yeah take second look, you'll find kind of yeah this compound actually the methyl compound. Okay, so there's kind of yeah mirror symmetry plan cut through this molecule, make half kind of mirror image into another half. Okay, so that's actually identical. Okay, so you can also run RS. Okay, so one comma R, one comma yeah another center kind of S. Okay, all right. So now we move to kind of yeah little bit harder one. Okay, please yeah work on kind of yeah question three. Okay, so yeah. Just indicate yeah whether these four molecule are kind of a methyl compound or not. Okay, yeah. So methyl compound yeah just yeah please keep in mind. Okay, so yeah that's here the yeah first, yeah, multiple cell centers, okay, two or more chiral centers, okay, you can call it chiral centers, okay. And then second, okay, so yeah, the whole molecule is kind of achiral, okay. As long as the one molecule, yeah, meet these two conditions, okay, that will be methyl compound. Yeah, take a look, okay. All right. We can also go through yeah, this four one by one, okay. All right, for the first one, okay, type your answer in the yeah chat window. Just yeah the yes or no. Okay. So are they is this one yeah methyl compound? Yeah, that's right. Yes. Okay. That's right. Okay. So there are two chiral centers. Okay, and then whole molecule kind of yeah a chiral. Okay. So yeah, that's yeah the yeah methyl. Okay. So yeah. Right. Okay. Also type your answer yeah, in the yeah window. Okay. So chart window. Is this compound methyl or not? Yes or not? That's right. Okay. So yeah, should be no. Okay. So yeah, this compound, okay, so yeah, there's no chiral centers, okay, so yeah, here's kind of yeah, no chiral center because there's kind of yeah, two same attachment, okay, no chiral centers, okay, yeah, no, okay. All right, okay, so now we move to next one, okay. The third one also type your answer, this compound, methyl or not. All right, okay, so yeah, no is the right answer, okay, so yeah, although this compound has the two chiral centers, okay, but there's yeah, no symmetry plan, okay, so you cannot cut through here, okay. So that means here the whole molecule actually chiral, okay. So chiral cannot yeah, meet the second conditions, okay. So yeah, chiral molecule, not methyl compound. Methyl compound is achiral, okay. All right, good, okay. So now we come kind of your most tricky one, okay. So the last compound is the methyl compound or not, okay. Type your answer in the yeah, window, okay. Last compound, yes or no. All right. Okay, pretty good. Okay, so yeah, you guys know the trick. Okay, so yeah, this compound is actually kind of yeah, the yeah, methyl compound. Right. The reason for that kind of yeah, if you take first look, definitely yeah, there are kind of yeah two chiral centers. Okay, but yeah, if you take first look, you cannot find any kind of yeah, simple plan in this molecule. Okay, but yeah, if you rotate the middle carbon compound, okay, so like 180 degrees, okay, so we just rotate right carbon, rotate 180 degrees, okay, this methyl group will go inside, and then this CSH will go kind of going down, okay, and clearly we can see kind of the symmetry plan, okay, so that means kind of two chiral centers, but whole molecule kind of a chiral, okay, so that should be kind of methyl compound, okay, all right, pretty good, okay. Share the slides, okay. Okay, so one tips kind of whether you can figure out kind of methyl compound node. Okay, so they have kind of identical chiral centers. Okay, so normally it's one is R, one is S. Okay, so and then the same set of substance group. Okay, right, and then here this one actually I already just talked with you guys. Okay, so there's one big types of question in the future exam quiz. I give you kind of two compounds ask you identify are they enantiomer, diastereomer, identical, and those concealed isomer. Okay, concealed isomer are pretty easy to identify. Okay, they have kind of different connections. Okay, and then different kind of position of functional group. Okay, and then more difficult kind of same connection. You have to look at kind of fair center kind of assignment. Okay, so if all opposite, okay, so enantiomer. If they are kind of some same, some different kind of diastereomer, and then if all are same kind of, that's we call kind of identical. Okay, and so let's do another practice. Okay, right. So please work on this four molecule. Okay, determine what's their relationship. Okay, so are they concealed isomer, enantiomer, diastereomer, or identical compound? Okay, so I give you guys kind of a couple of minutes. Okay, so that's one types of question you see in quiz full also in the future exam. Okay, so take a try. Okay, take a try. Okay. So if you can directly visualize the okay, so uh, the relationship between the two compounds. Okay, so are they kind of superposable? Are they kind of just mirror imaging, non-superposable? Okay, so that's the best. Okay, so if you cannot visualize the other relationship, okay, then you can design RS. Okay, you can do the RS assignment. Okay, and so uh, if all cell center opposite kind of alignment, okay, that's enantiomer, or kind of same, identical, some same, some different, okay, that will be kind of stereoisomer scale, diastereomer scale, diastereomer scale. Take try the last question in the worksheet. All right, okay, because of time limitation, okay, so we start go through them one by one, okay. All right, just type your answer in the chart window, okay. So for the A, okay, this pair, what's their relationship, okay? Are they enantiomer, diastereomer, or identical, or maybe just a concealed isomer? So most you guys get the right answer. These two should be enantiomer, right? So yeah, if you then RS, okay, definitely one is R, one is S, okay. So yeah, and another way you can do it kind of yeah, you flip one molecule, okay, you find there are kind of mirror imaging, but non-superposable, okay, non-superposable, okay, no matter kind of yeah, how do you rotate, flip it, okay. So yeah, right. Okay, so how about here the B, okay? Anyone can type your answer in the chat window. What's their relationship, okay? Enantiomer, diastereomer, or identical? Mm, yeah, that's right. Okay, so most students give kind of right answer. Okay, diastereomer should be right answer. Okay, so this one actually not too hard to figure out. Okay, so yeah, one chiral center here. Okay, you see kind of yeah same configuration, same configuration. Okay, so yeah, same configuration. Another one you find kind of yeah OH and methyl kind of yeah swapped. Okay, so yeah, if the swapped case, we know that kind of yeah generally the opposite kind of yeah configuration R become S, S become R. Okay, so that's yeah typical some is same, some opposite. Okay? Some same, some opposite. Okay, so that means kind of this molecule should be yeah diastereomer. Okay, yeah diastereomer. Okay, so yeah. Okay. All right, okay. How about C? Okay, so yeah, these two are enantiomer or yeah, yeah, diastereomer or identical. Mhm. So I saw kind of three different answers identical enantiomer, diastereomer. Right. Any other students? Alright. So this is the hard one. Okay. Give you answer should be enantiomer. Right. All right, so for this one case, yeah, one way to do is kind of yeah, you try to yeah, flip or kind of rotate one molecule, okay, yeah, for example, okay, I rotate yeah, the second molecule, like maybe yeah, actually I just yeah, flip it, okay, that's easier, okay, all right, so just flip this molecule like 180 degrees, okay, flip it, okay, all right, so once I flip it, okay, redraw it. Right. So this dash bond, okay, will flip to here. This wedge bond will flip here, become wedge, right? Okay, so that's your original, like this way, point towards you. Now flip it, okay, point away from you, okay. And same thing, okay, so yeah, this bond, okay, so yeah, will become kind of wedge. Yeah. And then you clearly see these two molecule mirror imaging, okay. If they are mirror imaging, cannot be diastereomer, okay. And then next kind of yeah, whether kind of identical or enantiomer, okay. So yeah, if yeah they're identical, so then yeah these two molecules should be superposable. Superposable kind of all the bonds should be matched, okay. So yeah, but yeah, uh, no matter how to kind of yeah rotate, okay, and also kind of how do you kind of yeah yeah flip it, okay always yeah these yeah two massive bonds won't match to each other. Okay, so always one going up, one going down. Okay, and then eventually these two should be kind of yeah non-superposable in mirror imaging. Okay, so that should be enantiomer. Okay, another way to do it kind of yeah you can go ahead and design RS. Okay, so yeah for example okay so yeah this one should go up. Okay, so that's here the S. This one also S. Okay, SS. Okay. Here, last here should be R and R. Okay. So you see kind of here the all the stair centers are opposite. Okay. So that's here all stair center opposite, we show kind of enantiomer. Okay. So that's here two way to do it. Okay. So either use an RS. Okay. Or kind of here just here the yeah. Try to imagine the case. So yeah. Right. Okay. So yeah, for the D. Okay. So last pair. Okay. So are they enantiomer, identical, or kind of here the yeah diastereomer? All right, put your answer in the chat window. All right, that's pretty good. Okay, so now you guys know the trick. Okay, so these two actually same molecule. Okay, yeah, pretty much they just the rotate one molecule. Okay, like 180 degrees. Okay, so that's this equator bond will here, and then this axial equator bond will move here. Okay, these two actually kind of same molecule. Okay, so that's identical. Okay, all right. Okay, good. Okay, pretty good. Okay. So now we continue our lecture. Okay, so the slides go back. Okay. Mm, okay, here. Okay. So so far we already learned kind of two ways to show the stereochemistry of the molecule. Okay. So one is using dash and wedge bond structure. Okay, line angle structure. Okay. And another one using a Newman projection. Here we will learn the third way called kind of Fisher projection. Fisher projection. Okay. So to draw the Fisher projection, okay, so you have to kind of a little bit align the molecule, okay, so a little bit kind of adjust okay, its position, okay. So you have to make sure that the horizontal bond, okay, point towards you and as a wedge bond, okay, so horizontal bond, okay, like here, okay, and then the vertical bond, okay, so that's going straight up, straight down, okay, so point away from you, okay, so that should be connected by kind of dash bond, okay. So once you converted the molecule, dash wedge kind of structure like this way, okay, and you directly kind of change all the wedge dash bond into straight line, okay. So that is called kind of Fisher projection, okay. So not only you can show one kind of stereocenter like this way, you can show kind of multiple stereocenters, okay. As long as kind of the horizontal bond kind of point towards you, okay, and then two terminal kind of wedge bond, okay, two terminal kind of dash bond point away from you, okay. Then you can directly show it as kind of straight line, okay. So in other words, okay, all the horizontal bond, okay, so actually you can also convert Fisher projection back to its the Weierstrass structure. Okay, just keep in mind, okay, all the horizontal bond. Okay, so that's like this. Okay, point towards you, and then all the kind of vertical bond actually point away from you. Okay, all right. So then kind of important thing is so you can rotate kind of the Fisher projection in 180 degrees. Okay, so 180 degrees. Okay, won't change kind of its configuration. Okay, but the 90-degree rotation and then 270-degree rotation kind of not allowed. Okay, so the reason for that that's actually you change kind of wedge to dash to wedge. Okay, that's change kind of stereochemistry. Okay, that's not allowed. Okay, so that's pretty important case here. And also in the future class, okay, maybe exam quiz, okay, so you should also able to assign kind of RS based on Fisher projection, okay, so give you one example, okay, so here. Right. So for example, this is the one Fisher projection, okay, and as you kind of assign kind of RS for the middle carbon stereocenters, okay. So you need always keep in mind, okay, the horizontal bond actually point towards you, okay, right, and then the vertical bond point away from you, okay, right. For this one, okay, so we still can assign the priority, okay, the highest one should be this OH group, okay, and then followed by this ethyl group, okay, so and then followed by kind of this methyl group, okay, right, and then you draw the arc 1, 2, 2, 2 to 3, okay. And it looks like clockwise, okay, but the hydrogen in the horizontal bond, okay, so that's actually point towards you, okay, point towards you, you need to give opposite assignment, okay, so that's the center for this one should be S, yeah, that's just please keep in mind, okay, so, and also a more difficult question, kind of probably in future there's kind of naming question. Okay, so you should also able kind of name kind of Fisher projection. Okay, and the Fisher projection actually pretty good to be used to the identify relationship between the two molecule. Okay, So for example, the first the two pair, okay, so first two molecule, okay. So you can clearly see kind of they are mirror imaging to each other and then non-superposable, okay, because R1 is R1, R1, R2, okay. And then there are kind of enantiomers, okay. And then second pair, okay, so you clearly see it's kind of one steric center, they have same pointing, but another one opposite, okay. So some same, some kind of different, that's their stereomer, okay. And also facial projection help you kind of identify kind of the meso compound, okay. So for example, this molecule, okay. So there are clearly there's the simple plane, okay, and then make the half mirror imaging to another half, okay. And there are also two steric centers, okay, two chiral centers, okay. This molecule is also kind of meso compound, okay. So that's a facial projection, okay. Yeah. All right, okay. So now we move to kind of a cyclic molecule, okay. And so for cyclic molecule case, we start from kind of two disactive, okay, disactive kind of cyclic structure, okay, with two different kind of the chiral center, two different chiral center means kind of two different substance group, okay. And so example here is kind of two methyl cyclohexene, okay, two methyl cyclohexene, okay. And so last comes kind of previous lecture material, okay. So for uh, cyclic molecule, we never use kind of cis trans to assign kind of stereochemistry, okay. A reason for that, that won't cover all the kind of stereochemistry, okay, steric isomers, okay. So here's kind of example, okay. So for the cis 2 methyl cyclohexene, okay. So and you can see there are kind of two structure, okay. Both are cis, okay. Both are cis, okay. And then they actually kind of enantiomer to each other, so, okay. So one's kind of RS, another kind of SR, okay. And the similar thing for the trans, okay. So two trans, okay. So there's also two trans structures, okay. So one's kind of SS, another's kind of RR, okay. So in other words, okay, so the two steric center relative to kind of the four steric isomers, okay. Two pairs of the enantiomer, okay. Two pair enantiomers, okay. So don't use cis trans kind of name the dissective kind of cyclo arcane, okay. So because you cannot cover all the situations, okay. So you have to use kind of RS, okay, and then then kind of the stereochemistry, okay. All right, okay, and so that's actually also the same situation for the kind of 1,3 dissective kind of cyclo arcane, okay. So totally two stereo centers, okay, and then four stereo isomers, okay, and then two pairs of kind of the enantiomer, okay, two pair enantiomer, okay. All right, okay, so here kind of two different kind of stereo center, okay. The tricky thing comes kind of two same starting group, okay, so still two stereo center, okay. All right, so like this one, okay. So one, two, dimethyl cyclohexene, okay. So you see kind of two stereo centers, okay, and then but there are kind of possibility for the meso compound, okay. So for the planar structure like this one, you quickly identify there are kind of simple plan, okay, cut through here, make one kind of mirror imaging to another half, okay. So this one should be kind of meso compound, okay. All right, but some students maybe quickly say like, okay, so we know that here for the cyclohexene, that should be kind of a chair conformation, okay. So in the chair conformation, you cannot draw the kind of simple plan, okay, because one the method will be kind of axial, one kind of the equatorial, okay. So that's definitely kind of not be kind of mirror imaging to each other, okay. No simple plan, okay. However, okay, so we can do the ring flip, okay. All right. So ring flip, okay, you change kind of equatorial to axial, axial to equatorial, okay. And because they are kind of two same starting group, okay. So that means kind of these two ring flip structure, they are kind of same energy, okay. One equatorial, one axial, okay. And 50% in the kind of solution, okay. And these two molecule mirror imaging enantiomer, okay. But in the solution, okay, so we are kind of 1-to-1 ratio, okay. So two enantiomer, okay. So in 1-to-1 ratio, we call kind of Raci mixture, okay. Raci mixture actually same behavior, same kind of the chemical physical property as kind of acyl molecule, okay. So in another words, okay, although the cis 1,2-dimethyl-cyclohexene, okay, so yeah, kind of yeah, yeah, two yeah enantiomer mixture, okay, but overall, okay, in general, okay, so that should be A chiral, okay, A chiral, okay, because kind of yeah, the two enantiomer 1-to-1 ratios, okay, so that two should be kind of yeah, yeah, A chiral, okay, so yeah, A chiral, okay, so yeah, yeah, so conclusion here, okay, conclusion here, okay, so yeah, yeah, for the yeah, cycloalkene, especially cyclohexene, okay, so yeah. The yeah, planar structure, okay, give you kind of right yeah the conclusion, okay. So yeah, if planar structure shows A chiral, then whole molecule should be also A chiral, okay. Yeah, just yeah, don't worry about kind of yeah chair conformation, okay. And the same thing for the kind of yeah the yeah trans yeah the 1,2-dimethyl cyclohexene, okay. So yeah, all right. So yeah, trans yeah definitely you cannot find any kind of simple plan, okay. So that means kind of yeah the yeah trans yeah that should be kind of A chiral. It has kind of it's enantiomers, okay. So yeah, one's kind of R, one's kind of SS, okay. And so yeah, if you draw is kind of yeah the chair conformation, okay, and then yeah you find kind of yeah the yeah we just use 1R, 2R as example, okay. So yeah, you find kind of yeah both yeah the yeah methyl group in the equatorial positions, okay. So yeah, if you do ring flip, you put kind of both on kind of axial positions, okay. So that's yeah, extremely unstable, okay. So that means in the solution, 99% time kind of yeah this yeah the 1, 2 yeah 1R, 2R kind of a 1,2-dimethyl cyclohexane, okay. So we will stay in kind of yeah diaxial, okay, di-equatorial positions, okay, di-equatorial positions, okay. So 99% time, okay. So this is chiral molecule, and then that's yeah the yeah means yeah the original kind of yeah cyclo yeah the yeah hexene kind of yeah the yeah structure also kind of chiral, okay. The planar also chiral, okay. So yeah. So yeah, another thing, yeah, please keep in mind, okay, so yeah, if you do the ring flip, okay, won't change kind of your stair center assignment, okay. So if it's RR, it will be still RR, okay, and then if it's kind of SS, to be SS, okay. So yeah. And the conclusion here is kind of yeah, yeah, for two yeah same cycle group, okay, two same cycle group, okay. So yeah, cis will be methyl compound, trans will be a pair of enantiomers, okay, a pair of enantiomers, okay. And for here, you just yeah make sure you use kind of yeah the plant structure. Don't need to draw the chair conformation. Okay? Plant structure give kind of yeah right conclusions, right conclusions. Okay, so yeah. All right, so now we move to the yeah, last yeah, the yeah, cyclic molecules. Okay, so yeah, the yeah, 4-methyl cyclohexene. Okay, so yeah, that's yeah, 1,4. Okay, all right, and so yeah, for this 1,4 dissective situation. Okay, so there's no cell centers. Okay, no cell centers. Okay, so yeah, right, because that's kind of yeah, simple plan. Okay, cut through. Okay. And then yeah, question kind of yeah, how many kind of yeah stereoisomers? Okay, so stereoisomers. Okay, so yeah, the yeah should be two. Okay, so one is kind of cis, one is trans. Okay, so yeah, the last one kind of yeah cis, right one is trans. Okay, right. So what's their relationship? Okay, so their relationship actually kind of yeah diastereomer. Okay, so that's yeah pretty interesting case. So, yeah, the diastereomer no not to be kind of yeah chiral. Okay, so yeah yeah they can be achiral. Okay, but yeah the still diastereomer. Okay, so yeah one stere kind of yeah the diastereomer is kind of yeah some kind of yeah same, some kind of opposite. Okay, so something some opposite. Okay, so yeah the methyl kind of opposite, and then the OH kind of yeah opposite. Okay, so yeah that's yeah diastereomers. Okay. And the same thing kind of yeah, yeah for the yeah if it's kind of yeah two same attachment, okay, for them kind of yeah maybe just see the get out, okay, yeah, the same thing for the yeah two same attachment, okay, yeah, one for dimethyl, okay, so one's kind of cis, one's trans, okay, so both kind of achiral, okay, because yeah if you draw the kind of yeah yeah that's kind of clearly you can draw the kind of yeah simple plan, okay. And but yeah, their relationship, okay, so that's kind of yeah two yeah two stereoisomers, okay. So that's yeah still kind of yeah yeah diastereomer, okay. Yeah, so they are two different compounds, okay, and then but yeah they are not yeah they are kind of yeah yeah stereoisomer, but yeah yeah not enantiomer, okay. That's yeah we call kind of yeah diastereomer, okay. Right, and then last thing for this class, okay, so yeah, in future, okay, so yeah, if in exam quiz, okay, so yeah, show you kind of yeah two chair conformations. Okay, so yeah, the easiest way is kind of to do is kind of yeah convert to yeah the yeah uh kind of yeah the planet structure. Okay, and then you can have kind of use IRS also kind of yeah identify the relationship. Okay, so give you quickly one example. Okay. All right. Okay. So for example, okay, so in exam quiz, okay, so I show these two molecule as kind of yeah, what's their relationship, okay? So yeah, they're similar or enantiomer or kind of identical, okay? So it's hard kind of yeah the identify by kind of yeah the yeah chair conformation, okay? So yeah, easy way is kind of convert them to yeah the yeah planar structure, right? So this one going up, that should be kind of wedge. This one going down should be dash, right? Similar thing, okay? So yeah, another one that should be wedge. And then this one should be dash. So once you are converting this to yeah, yeah, kind of yeah, yeah, vast dash structure, also kind of yeah, plant structure, okay, that's yeah, pretty easy to identify what's their relationship, okay, so yeah, right. Can anyone tell me what's relationship between these two? They're similar, enantiomer, or identical? You can type your answer in the yeah, chat window. Yeah, what's the relationship between these two? Hmm. Why enantiomer? All right. Identical should be right answer. All right. So yeah. So this one, okay. So yeah. You can line RS, okay. Line RS, okay. You'll find kind of yeah. This stair center come up same. This carry center will come up same. Okay. Another way, okay. Another way is kind of yeah. You flip the molecule. You flip the molecule, okay. So for example, yeah, yeah. I just yeah flip yeah this molecule like 180 degrees, okay. You flip it, okay. Flip it, okay. So once you flip the case, yeah, this yeah, the methyl group will become wedge. This OH group will become dash. Okay, so go here. And then you find kind of yeah, these two actually same molecule, okay? Yeah, same molecule, okay. So yeah. All right, so this is a hard question. Okay, so yeah, the I will give you some kind of homework assignment later today. Okay, you guys do more practice, do more practice. Okay, so yeah, if you have any question, okay, just here yeah, let me know. Okay, so yeah, yeah, so yeah, by the way, okay, so yeah, if on Monday, okay, so if on Monday there's another snow day, okay, and so we'll continue our lecture on just yeah Zoom, okay, so through Zoom, okay, and then the quiz yeah four will be on Wednesday, okay, so yeah, that's yeah, just let you guys know, okay, right, okay. Thank you guys. Okay, hopefully you have still learn something through the Zoom lecture and then have a good weekend. Okay, right. Thank you. Okay, bye guys. Yeah, yeah. Have a good day. Yeah.